Cool. Morning, everyone in New Zealand, and good afternoon, Monica. Good day to the people from other parts of the world, if any. Welcome to the CRISiSLab webinar. We invite speakers from all around the world to share their newest findings and knowledge regarding earthquake early warning. We have been organizing webinars, workshops, or similar engagement activities for the community of practice regularly. To those who are new today, welcome to join us. My name is Alicia Cui, a research officer in the Joint Center for Disaster Research at Massey University. I will do a brief intro and Dr. Marian Tan will be facilitating the question session. Today, we're very glad to have Monica Kohler, research professor at California Institute of Technology, and to share the vision and development of the project, Community Seismic Network and Earthquake Early Warning. We're very excited to hear all about it. So the webinar will be lasting for 1 hour, and you can see the agenda here. So there will be 20 to 25 minutes of presentation, and everyone will have chances to ask questions. Please be mindful of the virtual etiquette, and please put your name on the screen, and feel free to use chat box to introduce yourself, i.e. your name, title, and organization. And you can use chat box to ask questions or raise your hand afterwards during the Q&A session, or like Monica suggested, you can interrupt her. Cool, so without further ado, let's welcome Monica Kohler.
Thank you very much. Give me a second to bring up my slides. Sometimes it takes me a few seconds to bring it into a slideshow mode. There we go. All right. Thank you so much for that nice introduction, and thank you for introducing me and inviting me to give this talk. When Caroline first asked me to give this presentation, I had to explain earthquake early warning is not my primary research topic. I have done work in early warning, mostly on the project management side, but really I'm a kind of a seismologist and earthquake engineer by training and by trade. And so what I thought I would do today is talk about Community Seismic Network and its role in earthquake early warning. But I am going to take the majority of the talk, or the first half or 2/3 of this talk, to actually present Community Seismic Network in general, kind of our development of it and some of the data sets that we've recorded from it. And then I'll introduce how we're using it in test instances of 2 of the algorithms used in the Shaker Earthquake Early Warning Program on the west coast of the United States. So let me just, okay. All right, so you see here under these 4 points, the main mission for Community Seismic Network. I'm going to refer to it as CSN. It's a low-cost MEMS sensor and cloud-based, particularly AWS, strong motion seismic network that has these 4 goals that are part of its mission. You can see here that it's focused both on ground motion products as well as structural health monitoring products, and I'll get into a little bit more of both of those in this talk. The website is listed here, csn.caltech.edu, and I want to acknowledge members of the Community Seismic Network team. This is the current team. Of course, the membership has evolved over the years, especially as graduate students and undergraduates have become involved and then graduated, but this is the team as it exists today. So I'm trying to forward my slides, and for some reason they're not moving.
Maybe you can exit the full screen and move on.
Yeah.
The other thing I find is you have to click in the screen. Somehow, whenever I do stuff, I have to click in back in the screens again.
Okay, so I don't have to explain to this group how earthquake early warning works, but specifically for the states, the West Coast states of the United States, the networks that exist along those states first record the P wave, and they use information from the P wave to then make a prediction for when the S wave will arrive. But more specifically, the Shaker Earthquake Early Warning System focuses on making estimates for the ground motion in various areas that will be affected when that ground motion estimate is over a particular threshold. And so in the United States, in the west coast of the United States, this map shows the location of all the stations that are contributing data to the earthquake early warning system. These green triangles represent the stations from the US Geological Survey ANSS network, and they make up 3 regional seismic networks that are run out of Pasadena, out of Berkeley and Menlo Park in Northern California, and Seattle in Washington. And this map shows the stations as they existed as of May 2019, but the configuration and number of stations today is pretty much the same. The alerting region for the West Coast is shown by the dashed red outline. And so, as you can see by this map, not all of the stations are required to be within the alerting region, and that's especially important for earthquakes that occur near the edges of this alerting boundary, particularly in Nevada and in Idaho, where the seismic network's density, when it goes way down, the alerts tend to be less accurate. So having an alerting region that encompasses all of the stations leads to better alerts. But along the west side of the alerting region, you can see that the alerting region occurs in the Pacific Ocean, and that is also done on purpose for a couple of reasons. The first is so that it can accompany or encompass all of the stations that occur on some of the islands that are offshore Southern California, as well as include some of the tectonic regions, for example, the Cascadia subduction zone that is offshore Oregon and Washington here along the west side of the West Coast. So this slide shows a summary of how the shake alert system works. And it's busy. I know it's busy, and that's actually part of the could potentially be part of the problem that I'm going to describe in just a second, that led to the development of the community seismic network setup. I do want to go over a brief summary of this slide to explain the motivation for why we set up community seismic network data for shake alert a little bit differently. This slide shows, if you kind of start from the bottom and move your way up, what this slide indicates is that at these 4 seismic network alerting regions occurring in Seattle, Pasadena, Menlo Park, and Berkeley, all of the waveform data from all of the seismic stations used in earthquake early warning are sent to one of each of these reporting regions, these processing networks. And then from there, the waveforms are processed by 2 different algorithms. The finder algorithm, which is used to do finite fault source characteristics, and the epic algorithm, which does point source characteristics. The information from the output from each of these algorithms is then sent to an active MQ broker, which is just a message passing software that exists separately at each of these reporting networks. That information is then sent to another broker in which the ground motion, that's what GM stands for, the ground motion estimates are made from the products that come out of the 2 algorithms. Those products then go through another algorithm that's called the solution aggregator. And it's at this level here where you can see that the information that comes out of this solution aggregator is shared among the different regional networks. Within each of those regional networks, then the products go to a final broker, out of which another algorithm called the decision module packages the final solution into a product that is then sent to the outside world, the subscribers or the general public. So it's pretty multi-layered. It has a lot of different moving parts to it, but it's particularly at this lowest layer, this layer that describes how all the full waveforms are received at each of the regional networks, that is a potential problem for doing earthquake early warning in the United States. So specifically, 2 years ago, when the 2019 magnitude 7.1 Ridgecrest earthquake struck Southern California, it occurred about 200 kilometers from the downtown Los Angeles area in a tectonic region called the Eastern California Shear Zone. It was discovered that stations in the epicentral region near Ridgecrest experienced such large time latencies that it made those stations useless for estimating the initial source parameters for the Ridgecrest earthquake and the alert region, because the data arrived, that is the full waveform data arrived at the Southern California Seismic Network Processing Center too late. And after quite a lot of investigation into why these large latencies occurred, it was discovered that these large latencies, 5 seconds or more to several minutes, occurred for a multitude of different telemetry types. They occurred for cellular, for radio, and for satellite telemetry, although it didn't, the large latencies didn't occur for stations that had direct high bandwidth connections. The investigations showed that the weak and marginal radio connections were also vulnerable to increased latency because of the increased demand for sending the data from the epicentral region to the data processing center. And finally, on top of all of that, it was discovered that data logger data compression inefficiencies occurred. And so this likely added to a large latency issue. So these kinds of issues were anticipated when Community Seismic Network was first developed about 9 to 10 years ago now. It was this, we knew that once we were able to deploy sensors so that we have a denser network than what currently exists, that sending full waveform data for algorithms like earthquake early warning algorithms that require very, very small time latencies could be potentially a problem. So Community Seismic Network was developed in such a way that the sensors in the field, indicated by these orange boxes here in the upper left, either at ground level locations or in upper floors of buildings, would send data 2 different ways. They would send parallel data streams, indicated here by the black and the red arrows, where one data stream consists of instantaneous, very small scalar, time-stamped peak amplitudes, specifically acceleration amplitudes, if their amplitudes exceed 0.5% G. And at the same time, there would be a parallel data flow architecture in which full waveforms are sent, but they're sent in 10-minute chunks. So the instantaneous time-stamped peak amplitude scalar data are the real-time data that would be used for things like earthquake early warning. And the 10-minute waveforms are the near real-time parallel data flow that would be used for things like structural health monitoring experiments. And so that's indicated here. Oh, so the other way that the architecture was developed that is different from the way that seismic networks run today is that rather than sending all of the data to a central archive that is somewhere on site, say at the Caltech campus or at the USGS Pasadena location, they would all first be sent to the cloud in order to get away from sending all the data to the same site that may be affected by a strong earthquake. And then do some minimal processing in the cloud before then sending the data onto the algorithms that produce these products. So with these 2 data streams, you can see indicated by the arrows here that the very small scalar instantaneous peak amplitude data are sent through, and this is the way it occurs today, are sent through a lightweight server that's running in AWS. They're sent through one of these active MQ brokers, this message passing software broker. And the data are being sent into a demonstration instance of ShakeMap, a demonstration instance of ShakeCast, which is a building-specific fragility analysis piece of software, and into demonstration instances of Finder and Plum, which is another earthquake early warning algorithm that's currently in testing and that will probably be in production in a year or so. And then separately, and not really as relevant for this talk, the full waveform data are then sent to a server at Caltech where they're archived, and then those data are used in separate structural health monitoring and damage detection experiments. So this slide, this is a slide that was made by a colleague of mine, Rob Clayton, several years ago. And this slide just kind of provides a schematic motivation for why develop low-cost sensors such that one can deploy them in great density in areas that are at risk for strong motion earthquakes. And this is just one way to show that. At the top, you see an estimate for what the perfect wave field should look like at, say, 1 hertz or 0.5 hertz as it's propagating throughout Southern California. The scale of this map is roughly 30 kilometers by 30 kilometers. With the current array in Southern California, where the station spacing is 5 to 10 kilometers or so, this is what the waveform actually looks like when you look at how the current array configuration samples that wave field. And by the way, you could think about this in terms of site amplification effects too. How does the current station configuration affect or capture site effects? But if we have 1,000 stations in this, say, 30 by 30 kilometer region, this is what the wave field would look like captured by this much denser array of stations. So getting back to the Community Seismic Network, this is a map of Southern California. You can see the distance marker down here for where we currently have stations. We have stations, over 700 stations, about 720 stations that are at about a half a kilometer spacing. And our stations are deployed mostly at school campuses, public school campuses. There are a few in civic buildings, some in office buildings, including multiple floors of a few high-rise buildings. We have about 200 stations that are at the NASA JPL campus, which is right here. So it's kind of our array within an array. And very few of our stations are in private homes. The triangles on this map indicate the regional network, the Southern California Seismic Network. So the array of stations that we have now by CSN deployments kind of gives you an idea of how we have kind of an order of magnitude denser deployments of these stations relative to the background, the regional network. So I want to first start with the hardware behind the network, and this is really the more mundane aspect of CSN. It's all our parts are commercial off-the-shelf parts. A lot of focus goes into discussions on how this hardware operates, and I'll get into that. But I would say it's commercial off-the-shelf hardware, and that's on purpose. We want to have low-cost hardware, and I would say that all the parts that go into one of our seismometers, one of our packaged units, which is kind of indicated here, comes to about $300. So we record continuous acceleration time series on our MEMS triaxial accelerometers at 50 samples per second. Actually, the initial sample rate is higher than that, and then we downsample to 50 samples per second. And timing is controlled by NTP time, on top of which we make a couple of other additional timing corrections by linear regression analysis. We have an onboard processor that is a Raspberry Pi, and you can see the specs provided here. We have backup power and battery backup at each of the sites. All data flow is done through Ethernet connections. We do have one or two cell modem setups, but the majority of our stations are Ethernet. And the accelerometer chip itself is made by MEMS, ST Microelectronics, and it's packaged up by a company called Fidgets.com, from which we purchase these chips already packaged together. But we, as a CSN team, package up all of these hardware parts into this orange box. And I probably don't have to tell you, this group, the background of the MEMS sensor development. We use, again, commercial off-the-shelf MEMS sensor parts, and they are the same kind of MEMS sensors that are used in, for example, automotive systems. For example, the kind of accelerometers that you find in airbag systems in cars, and the same kind of accelerometers that are used in video game remote controls. So I mentioned there's quite a lot of discussion about how good are these accelerometers really. And we've had the opportunity to do quite a lot of side-by-side tests of the CSN MEMS accelerometers with other units, for example, the Kinemetrics epicensor. And so that's what this plot shows here. This is a side-by-side comparison of the data from a CSN MEMS sensor that was located in the same vault. These vaults are about 12-foot deep vaults located on top of a concrete pier on which there was also an epicensor deployed. This is for those of you who know the Southern California Seismic Network, this is the Pasadena station that's just west in the foothills, just west of the Caltech campus in Pasadena. And so these are waveforms from the magnitude 7.1 Ridgecrest earthquake that had occurred at a distance of about 185 kilometers from this vault. So here, what you can see are waveforms from the epicensor east-west component, the CSN east-west component, then the epicensor north-south, CSN north-south, and the epicensor vertical and the CSN vertical. And the vertical axes are all the same. They're all the same scale of acceleration. So you can see that the motions, even though they're very visible, were not that large in Pasadena. And the horizontal time scale is, scale is time. And so what you see very clearly are the arrival of the P waves, and then the complex train of shear waves, and then surface waves after that. And for any frequencies, lower than about 1 or 2 hertz, you can see a very clear comparison, almost wiggle by wiggle, between the epicensor recordings and the CSN MEMS sensor recordings. And what's kind of interesting in a plot like this is these plots also give an indication of what the ambient vibration kind of noise levels are in the MEMS sensor as compared to an epicensor. Getting a little bit more into the specifics of the sensitivity of the different pieces of hardware, This plot shows octave-wide bandpass acceleration from ambient vibration data from an epicenter from one of our CSN fidget sensors, and comparing that to an Android phone. And so you can see, and the horizontal scale is frequency. And so you can see how the SENS, or rather the CSN MEMS accelerometer lies roughly in the middle, about 3 to 4 orders of magnitude worse than an epicenter performance, but 2 or 3 orders of magnitude better than an Android phone performance for a pretty wide frequency response scale. And what you can also see on this plot are various curves that show the expected ground motions for different earthquakes, for near source earthquake at a distance of about 10 kilometers versus a regional earthquake at a distance of about 100 kilometers for different magnitudes indicated by these M values here, and where we might expect each of these types of sensors to perform. And so one way to interpret a plot like this is, let's say we're interested in for example, a 1 Hertz response. Epicenter will be sensitive to magnitude lower than 1.5 for both types of earthquakes. CSN MEMS sensor will be sensitive at around 1 Hertz to earthquakes of magnitude less, or rather greater than about 3.5. Which is consistent with the kind of earthquakes that we've recorded on the CSN sensors, as opposed to an Android phone where you have to wait until you get to magnitude 5.5, 6 or above in order to have sensitivity at 1 Hertz. And then this plot on the right just shows an ambient vibration set of time series for CSN sensors in the vault, indicating that our level of sensitivity here is about 100 microG. And this is internal hardware noise. It's not due to external noise at this point, because the Pasadena Vault is a very quiet location. So what do these data look like for an earthquake? I mentioned we've recorded the 2019 magnitude 7.1 Ridgecrest earthquake on many of the CSN sensors. The CSN sensors are indicated by the red triangles here on the lower left of this map. And Ridgecrest was up here about 200 kilometers away from downtown Los Angeles. And this movie just shows ground displacements that were recorded through double integration of our CSN sensor recordings in the kind of an area that encompasses most of these red triangles. And so in this movie, you see displacements. The circle locations are indicating displacement, and the colors of the circles are also indicating displacement. And so what you can see very clearly in this movie are both the P waves and the S waves coming through the CSN array, where the stations here are about a half a kilometer spacing, as the Ridgecrest motions are making their way through the upper northern half of the Los Angeles basin. What the other interesting you can see from this movie is that so these mountains here kind of separate the northern Los Angeles basin from the greater Los Angeles region north of this little mountain range here. And so the locations of these stations are in the mountains and out of the Los Angeles basin, and they're quieter. The site amplifications and the accelerations recorded here are smaller than the accelerations recorded in the northern Los Angeles basin. And particularly resonance, you can see resonance occurring for a long time in the northern LA basin after the first waves from Ridgecrest hit those stations. So if we look at something like pseudospectral accelerations at a couple of different periods, 1 second on the left and 3 seconds on the right, this gives you an idea of the variations in ground motion that occurred from the Ridgecrest earthquake that might be expected on a very dense array of sensors like the CSN sensors provides. The reason that I wanted to show these plots is that because earthquake early warning, at least in the shake alert system, provides an estimate for ground motion, dense networks like CSN begin to give you an idea of what the lateral variations in ground motions will be across very short spatial scales, because we now have the sampling from an array to give you that variation in sampling. In these plots, the circles are the CSN stations, and the Southern California Seismic Network, as well as another strong motion network operated by the state of California, is given by the diamonds. All right, so back to earthquake early warning. and how CSN is processing data for earthquake early warning. I mentioned at the beginning of the talk, it's not my primary area of expertise. And on top of that, we're still in the test instance of figuring out how to use CSN data in earthquake early warning. So we're not close to being in production level yet. I would imagine that might take a few years to get to that point because one has to go through quite a lot of formal testing before getting into production. But here is how we have set up our data pathway to get into the earthquake early warning algorithms in such a way that we can greatly reduce those latencies that were already seen for limited data for the Ridgecrest earthquake from the Southern California seismic network. So I mentioned that we have the seismic sensors in the field, and we're sending data to two algorithms, the Finder algorithm, which is currently in production, although it's not using CSN data in production, and another test instance of the Plum algorithm. The nice thing about testing the Plum algorithm, which with CSN data, is that the Plum algorithm, it does calculate source characteristics for earthquake early warning, but it also has the feature that it uses the propagating wave results. So it uses data from sensors that are not necessarily near the source, the earthquake source, to then make a prediction for what the ground shaking will be even beyond the propagating wave. And so Plum has the potential of using CSN data in the field that are not necessarily near the epicenter to make better, more accurate predictions for what the ground motions would be as the earthquake itself is, as the wave field itself is unfolding from the earthquake. So we have our sensors in the field, all triaxial accelerometer sensors that are sending these two parallel data streams. And so here, what I want to focus on is the FAST, the red arrow, FAST peak acceleration amplitude data. When these peak acceleration amplitudes are computed, they're computed from the time series deviations from a long-term mean that's calculated over 10-second sliding windows. And this calculation is done on the processor, the Raspberry Pis, at each of the sensors in the field. So you could consider this sort of an edge computing type of architecture. Each of the orthogonal axes is treated independently, and the minimum repick interval is 1 second on the same axis. So what that means is that you can get as many as 3 picks within each 1 second window. We call them picks, the peak amplitude calculations. And the CSN client, the software that's run at each of the stations, directly generates this active MQ message, that is the peak scalar amplitude, along with its associated timestamp, and sends that to the server in the cloud. The peak amplitude scalars are only sent if they're over 0.5% G. So this is partly to reduce some of the picks that are produced at the sensors that are not associated with an earthquake, and partly because the earthquake alert, the earthquake early warning alert, is only interested in those intensities greater than what might be useful for an earthquake early warning alert to the general public. So then those products are sent to the test instance of Finder, the finite fault algorithm, and the Plum algorithm. We've set this up and we're running this currently in this configuration. And so we actually don't have any large earthquakes that have occurred near the CSN station array that were actually large enough to produce a public alert for earthquake early warning, at least in the last 2 to 3 years. So while I don't have any results for an actual alert that might have gone out, we use the CSN data in replay mode to test what the alerts could look like with CSN data ingested into those public alerts. And so the map that you see here is just a result of one of those replay tests. This was a little earthquake that occurred about a little more than a year ago, on the west side of Los Angeles, indicated by this red star here. And so what we did here was we ran Plum in replay mode, where we used MMI thresholds, so shaking intensity thresholds of 4 for the first station and then 3 for the second and beyond station to produce a Plum alert. And what we found when we ran this in replay mode was that a detection was made about 4 seconds after the origin time, and Plum made an estimate that was off by about 3 kilometers from the true epicenter location. And the way that the data were ingested into Plum, again in replay mode, was that all the picks from CSN are ingested into the algorithm, but when they don't exceed a certain threshold, when they're relatively small, which is kind of indicated by all of these measurements that occur before 0, which is event time, they're not taken by Plum. They're not used by Plum because they're not associated with any one event and they're too small. But then by the time they've exceeded that certain threshold, they're then used by Plum to make an alert, to come up with the source characteristics, and then make estimates for ground motion prediction ahead of the unfolding wave. And so these are the results for using using CSN data that did record this 3.7 magnitude event about a year ago. Of course, that was replay mode, so that doesn't show what the latencies will do. And we actually don't know yet how the station scalar data flow will work in terms of latencies, because we don't have yet an event that was large enough to use in real time. But one of the ways that we have estimated the latencies for our peak amplitude data, and then comparing that with the Southern California Seismic Network, is to look at latencies for incoming data into the Southern California Seismic Network, and then compare that with the latencies produced by a ping command produced by the CSN stations. So this plot shows expected latencies. This was calculated about a little bit more than a year ago, for 331 Southern California Seismic Network stations, actually during quiet time, not during an earthquake. And so what this plot shows that while the majority of stations do have very small latencies for sending the full waveform data to a central processing site, there still is a fairly large handful of stations that have relatively large latencies on the order of seconds or many seconds. And all of these stations that are beyond just a few seconds would be too late to be used in an earthquake early warning product. And if we compare that with the kind of latencies that we might expect from CSN stations, we see here, by the way, we conducted this test experimentally by sending a ping command from a server at Caltech to all of the CSN stations, because the ping command is our proxy for how fast we might expect this small scalar to come in from the stations. For the ping command, sent from 328 stations to the central server and back, or rather from the central server at Caltech to the 328 stations, we find that the latencies for these stations is on the order of only about 55 milliseconds. And this largest latencies at 50 or 55 milliseconds occurred for a station that's located in Jackson Hole, so 1,200 kilometers away. So we would expect that the latencies are going to be a lot smaller. So I mentioned this is a configuration that we've set up relatively recently. We're kind of in ongoing monitoring mode. And so we're sort of waiting for the event to occur that would produce a public product to see how CSN station input would monitor and how it might modify that product and how it might change latencies from the data. And so here I've just kind of provided a summary for what are the paths to implementation for data from a CSN type of array. We do need to continue monitoring our test instances of the Plum algorithm and the Finder algorithm, currently set up at servers at Caltech. And it would be even more helpful if we can use PGV calculations in addition to the PGA peak amplitude calculations that are currently done at the CSN stations. Also deploy new instrumentation on an as-needed basis in those regions where we don't have enough stations from the current regional network to provide coverage that we think we'll need around causative faults for earthquake early warning. I already mentioned that we think that if we can incorporate these sorts of data streams consisting of these peak ground acceleration or MMI values along with their associated timestamps, we might expect that the alerts will be faster and result in lower latencies. And this would be due to the low-cost nature of the CSN array, a more efficient and lower cost way to augment the networks and fill those geographical gaps in station coverage where we currently don't have enough stations to provide information about the epicentral regions. But in the case of Plum, which doesn't just look at the epicentral region, it looks at the propagating wave effects, could use information from dense networks that don't need to be near an epicentral region. One of the key areas, though, that we know is a vulnerability or a weakness that we have to address and are in the process of addressing is how do we accommodate the fact that there's higher noise at each of these stations? And one way that we've planned to do that is to set up an automated procedure for calculating background noise metrics and for determining, using this procedure, whether a shake alert station, and frankly, this could be applied to both the low-cost CSN type sensors, or it could be applied to a regional seismic network station. Use this procedure to determine how reliable a station is for using its data in earthquake early warning alerting. I have here use of a broker in the cloud to relay this information, but this is actually something that we've already kind of in the halfway point of setting up. The broker that is already set up in the cloud could also be used to relay information about noise metrics for each station, such that in real time, the earthquake early warning system could be used to determine whether a station is reliable or not. And then on top of that, if it's an automated procedure that has been set up, this could be done on a time evolving basis in which a time adjusted noise floor is assessed and then used or not in the earthquake early warning system. So I'm going to wrap up in just a second, but before I do, I just want to mention quickly that CSN stations are also located in a few high-rise buildings with 1 to 3 triaxial sensors on every floor. And so, for example, in this 52-story high-rise that's located in downtown Los Angeles, you can see that accelerations that were actually recorded in this building during the Ridgecrest earthquake, although they're very small at the bottom, grow larger as you go up the building. And so one can imagine that when you're focusing on accelerations that are recorded in high-rise buildings, whether it's acceleration or velocity, or in this case, displacement that's been obtained through double integration, you can imagine that if we have information about these buildings that are also instrumented with low-cost sensors, you can give additional information about earthquake early warning alerts in 3D. Namely, you could give products that are customized to the tops of high-rise buildings, in addition to what you might be doing for the ground floor levels. All right, so I'm going to wrap it up there by showing this slide, which just shows the team putting together some of these boxes before one of our latest deployments. The team here, you can see me and Tom Heaton and former graduate student Anthony Mazzari, Julian Bunn, Manny Chandy, and Rob Clayton. We literally do put these boxes together once we've ordered all the parts. And I'm going to use this chance too to give the CSN website URL one more time, and to provide my contact information if any of you would like more information about the CSN hardware or software or deployment information, as well as if you want information about the data that we have recorded. Thank you.
Thank you very much, Monica. Marian, I will give to you.
Yeah, so I think people have popped in some questions as you were speaking, but it was also interesting, and I didn't want to interrupt you. Yeah, and it's really thank you for that presentation. I guess we'll start with question on central processing. Have you identified any challenges or negatives when processing the data from a central location?
Have we run into any problems? So we don't do central processing, and that's sort of the point of this. We want to push as much processing out to the stations themselves. So much of the processing is done at the stations. We have some minimal time series processing, so the means are removed. There's a little bit of minimal filtering that's done, and that's where the peak amplitudes are calculated. They're calculated at each of the stations, and then that information is aggregated into the cloud. And then that is sent to the earthquake early warning algorithm, which uses that peak amplitude data to make an alert. I kind of glossed over the kind of processing that we do for structural health monitoring, because that's a very different beast. That's where we do use central processing there, but that's because that uses full waveform data in a very different way.
Thanks for clarifying that. So you mentioned earlier in your presentation, you also mentioned where these sensors are located, and Nicola asked, what's the choice or barriers that there are only a few sensors located in people's homes for the
privacy? Well, okay, so there are a number of different reasons, and it's usually not scientific. First of all, is privacy. We did start off by having deployments in people's homes, and we had them sign agreements in which they it had to be clear that they understood what was being recorded. But what we ended up discovering is that in people's homes, not only was there this privacy issue, especially if there were kids at home, it's something you kind of want to stay away from. People would turn off power at night. Our initial, before we started putting out these boxes, with all the parts inside the box. We had a unit that got deployed into desktops or laptops. That was a very, very early iteration on CSN. And when we had people plugging them into their laptops or desktops, they would shut off the units at night. They would shut off the desktop at night. And when the power got shut off, then we didn't get data. And they didn't do it on purpose. They didn't know what they were doing, but it was very difficult to stop that. So once we, discovered that this was an issue, but at the same time discovered that with the schools, for example, with the Los Angeles Unified School District, where all we had to do is have one contact to make hundreds of deployments, it just became an obvious switch. Do Los Angeles Unified School District campuses instead, you get a really nice geographical distribution because campuses are nicely geographically distributed. And you get away from that issue of people turning off their computers or, moving and not telling you that they're moving, or disconnecting the sensor and they don't tell you that they've disconnected the sensor.
I see. No, thanks. Thanks. That's quite interesting that, the issues, I guess, are not scientific, but more really privacy. When you were showing us the instrument earlier on, Amal's asking, why do you downsample to 50 hertz? And
that's two issues. There's no, strong scientific or engineering. Well, let me take that back. So the first reason is that, when you have data coming in from hundreds of stations, especially when we started this project 10 years ago, bandwidth was a worry, bandwidth and data storage. So, we're collecting terabytes of data a year. So it's a lot, even at 50 samples per second, because we're at over 700 stations, it's a lot of data. And it's still, archival is still kind of a worry. So we downsample to 50 samples as a very nice, what we think is a nice compromise between getting the full waveform data, getting the continuous data and saving all the continuous data, versus having enough bandwidth to do quite a lot of projects with, quite a lot of different types of analyses at each of the stations. Seismologists are usually very happy with 50 samples per second, and they're not generally, for a regional array like what CSN is, they don't generally want higher sample rates than that. The engineers typically do want higher sample rates than that. Although it's interesting because if you consider deployments, sensor deployments in mid-rise and high-rise structures where the resonance periods are 1 second or so, 50 samples per second still gives you quite a lot of information. So in theory, we could go higher than that. We could go to a higher sample rate. We just have to then worry about, bandwidth at the local community hosted site, and then total data storage from hundreds and hundreds of sensors.
Thank you. The next question is, so thanks for showing us that photo that you were packing the sensors, and thanks for extending to people as well to be able to contact you regarding software and hardware. But a question from Raj is the CSN sensor a proprietary product?
There's nothing proprietary about it, and if you go to our papers and PhD theses, the students' PhD thesis, you'll find all the information you need on how to put them together. So that's why I wanted to stress when I showed the hardware slide, the hardware part of it is, it's very straightforward, and you could buy all those parts yourself. You could put them together yourself. It's as I was mentioning at the very beginning of this talk, it's actually quite similar to a Raspberry Shake sensor. In fact, I wouldn't be surprised if the accelerometer is almost exactly the same. It's just that we don't have a weak motion sensor on the hardware box. The software is what is more unique. It's not proprietary in the sense that, so the computer scientists who worked on our project have worked on various iterations of the software. And I know that some of their software is available through GitHub. I don't know that the latest version of what we run at our boxes is proprietary. And so if anybody wanted to kind of deploy a few CSN boxes and run it, then we'd probably have to work together on how to actually deploy that software. But in general, a kind of a generalized version of the software is available on GitHub.
Oh, thank you. I'm going to jump to Caroline's question first, then we'll return back to some of the other questions. So Caroline asks, she's interested in collaboration between national agencies and community networks. Are there two Shake Alert systems, or is Shake Alert using CSN data and collaborating with CSN? How does this?
There's only one Shake Alert system. Yeah, there's only one Shake Alert system. That is, the Shake Alert system is the the collaboration between the three main universities, Caltech, UC Berkeley, and University of Washington, and the US Geological Survey, which also has offices in all of those locations, as well as Menlo Park. So there's only one Shake Alert. And I referred to Shake Alert, and I talked about Shake Alert because in the United States, at least, you know, in terms of these free products that the general public can receive, it all comes out of that one Shake Alert system. We are moving, you know, we're hoping that we can eventually get CSN data ingested into the Shake Alert system. We're not there yet, and we're not close to being there, because the Shake Alert system has a very formal, very kind of rigid, long time testing process that one has to go through to show that, you know, whatever new algorithm, or in our case, whatever new data stream you're producing, it can robustly be included in the Shake Alert system. So we are moving towards trying to get CSN data into Shake Alert, but we're not there yet.
Can I just quickly jump in?
Go ahead.
You would have been interested in having your micro network of early warning, let's say for California, or just for Los Angeles? Would you be interested in just having like a micro community early warning, specifically dedicated for, let's say, Los Angeles?
So that's a really interesting question, and it could work that way. For sure, it could work that way. I mean, you know, we're recording the P waves, and one could, you know, easily send out an alert once the P wave is picked up by the microarray. Technically, there's no reason why we couldn't do it. We just don't have somebody who actually wants to, you know, use the CSN sensors to do that. Funny that you picked that you asked that question, though. There is a high school student in Palos Verdes, which is a city near downtown Los Angeles, who worked on this very project. She gave a really nice presentation at SSA last year, and so we've invited her to our group meetings. She was doing exactly that with a little CSN-like array that she had developed herself. She had developed all the hardware. She had put and implemented some basic versions of some software that does, you know, earthquake type of calculations, and that's how she was running her network. And so we've invited her to continue working with us if she wants. And so there's one possibility for how somebody who might combine CSN-like data into a kind of a standalone array that does earthquake early warning that doesn't depend on Shake Alert. So yeah, technically, no reason why we have to go with Shake Alert. It just takes somebody to do the legwork on getting that going.
Oh, thanks, Monica. So we have a question from Luke, and I'm just going to ask the first question, and maybe after Monica, you've responded, Luke can also tell about his experience on running Pi on a MEMS sensor. Anyway, so just a clarification. So you're doing limited data processing analysis on the Pis and outputting that, but then you're also transmitting the full raw sensor data. So maybe a bit of clarification, Monica.
Sure. So we have these two parallel data streams I was referring to, and they send data kind of at the same time. So what happens is with the first stream is just these very short peak acceleration amplitudes that are calculated on the Pi. And so those are those really small scalar values I was referring to. Peak accelerations with their associated timestamps. And so those are sent immediately. If they're over 0.5% G, they're sent immediately. And those are the data that are used in the earthquake early warning algorithms, the test instances of the algorithms that we're running, as well as ShakeMap, actually. Then there's the other parallel stream, which is the 10-minute chunks of data that are sent. So the waveform data are constantly accumulated on the Pi, and 10-minute chunks of data are sent up to the cloud and then downloaded to a server at Caltech for more processing and final archival. So I referred to that 10-minute waveform data stream as the near real-time data stream because they're not as fast. They're full waveform. They're sent in, you know, every 10 minutes. But because it's 10 minutes long, that's too long a latency to be used in earthquake early warning. But they're done in parallel.
Oh, thank you. Luke, if you can unmute yourself and maybe explain a little bit about what you mentioned in the chat box and maybe your follow-up question.
Sorry, Alicia, just had to find the unmute. Monica, thank you. So you're not transmitting the complete raw data stream from the MEMS sensor, is that correct?
We are, but we're doing it in these 10-minute chunks that I was just talking about.
Right.
So we do transmit the full data, but it's not done in true real time.
Cool. And the real-time data is, so you're doing limited analysis on that, the peak acceleration above a certain level, and righto, cool. Thank you. It's just
right.
useful to compare from what I've done with regard to the sort of processing capacity of the Pis. So the Pis you're using, by the look of it, are early, like Pi 2s, that sort of thing?
Yeah, they're actually Pi 3s. Our latest
Pi 3s,
deployments use
okay.
Pi 3s and 3Bs.
Yep.
So yeah, I think that's the latest version of them.
Cool, thank you.
Cool, thanks, Luke. Raj, you had a few more questions that I might have skipped out. So if you want to take this time to ask that question from Monica.
Yeah, I put a few questions actually. So one of the things this about using Plum algorithm, Monica. So it's, if I'm not mistaken, kind of the original Plum, it suggests that maximum warning time you can get is like 10 seconds, right? That's what, I mean, if you read, so what we have been following Kodera's work. So with the processing time at central location, or even with what you are doing at the Pi, so you'll get some time deducted from that 10 seconds. So the warning window realistically you'll have less than 10 seconds. But what we have seen, people have expanded that to more than 30 kilometer radius. So from end users point of view, how you feel, I mean, will people, I mean, will they be happy by giving them less than 10 seconds? I know you can automate things with that, but for end users, for their safety actions, what do you think?
Yeah, I mean, that's a great question. And that's a good question for earthquake early warning in general. How useful is, 2 seconds versus 10 seconds versus 30 seconds? And that obviously depends a lot on your end user. And so, quite a lot of studies have been done on this. And, so if you're operating heavy machinery that takes a long time to shut down, 10 seconds isn't going to be that useful. But frankly, it's, are you going to, for example, power utilities, are they going to shut down heavy machinery in any case? It's not clear. Bringing trains to a stop, 10 seconds, I don't know if 10 seconds is long enough, but potentially 10 seconds and less might be able to bring, trains and subways and things to a stop. There are a lot of applications, though, where it seems like less than 10 seconds is actually quite useful. And, a few come to mind that are usually used as examples are stopping elevators at the nearest floor. One doesn't need a full 10 seconds to stop an elevator at the nearest floor. Keeping garage doors of fire departments open so that the trucks can get out. If you have utility workers that are in the bucket trucks, and they're already raised up doing work on a utility line, a warning like that could simply bring the bucket down so that they're closer to the street and not up at the bucket at high elevations while the shaking is occurring. So even without thinking about automation of reaction to an alert, I think that the number of applications that don't need really long warning times is actually quite high. Not to mention the whole psychological aspect of giving people a warning that there's impending shaking, just to kind of give them a few seconds warning. Okay, something's coming. Don't panic. Do your drop, cover, and hold on, or whatever you've been trained to do in the few seconds that you have to do something.
Yeah, one other question I had is again related to this, because we are also kind of working with Plum. So what's now at your with AWS server, it will take some time for you to process, even though you are processing it some at the edge. So you lose some time. So what's the kind of time you take to process until you send kind of develop the alert?
So we've done tests on that. And by the way, Julian Bunn, who's probably been co-author in some of the papers you've read on Plum, he's the one who's doing the CSN work with Plum. And he's done some tests on that. And so if you send data through the cloud, there's very, very little latency associated with that, because the data packets are so small that it's transferring them around is very, very small. The only way that you would lose significant latency on that is if the AWS server itself is not available. And so for Plum, the peak amplitudes are all that has to be done with them is to turn them into MMI estimates. So it's kind of like a one line calculation in the code, which then makes them usable for Plum. So the latency for CSN data is and going through the cloud is very, very small. We would expect, and based on our tests, is very, very small compared to what the Plum calculation for any sort of data is at the Plum, algorithm running end of things. In other words, the latencies really build up when you have to wait for the full waveforms to come in, as opposed to the scalar amplitude values.
Yeah, I have a few other questions. I mean, we can chat later. So
Yeah,
sure.
Thank you so much.
Thanks.
Yeah.
Thank you, Raj, for those questions, and Monica. And I guess we have one more question, I think, one question just to wrap things up. And this comes from Hamish. And how are you handling false alerts or misalerts from the perspective of the costs and risks to the community?
I mean, that's a really good earthquake early warning question in general. And so one of the issues we have is that we actually haven't had very many earthquakes since the CSN deployments were made. So we don't have metrics on false alerts or missed alerts. But the test platform that was set up through earthquake early warning, that the official Shake Alert site does that, and it does it very well. So once we have more events that have been recorded by CSN, we can actually run it through the test software to generate, get an idea of what the false alerts and the misalert rate will be. So I don't have an answer to that. We just don't have enough data to do that, robustly. What I will say, though, is that I can imagine that if and when CSN data are ingested into Shake Alert, they are almost certainly not going to be used as the primary alert stations. They would be used as secondary or even tertiary alert stations, which is to say, wait until you think you do have a true event from, the backbone network, and then use the CSN data to update your alerts as you're going along. So, yeah, sorry, I don't have a really good answer on that because we haven't done those metrics.
Well, thanks, Monica. And I think we're pretty much just at 11, and just really want to echo what everyone's saying on the chat. It was a really great presentation, very engaging, and thanks for answering the questions. And and thank you. And if everyone would just like to help me thank Monica, if you have like a little clap icon.
My pleasure. Yeah, feel free to contact me if you have follow-up questions.
Yeah, great. Anything else, Alicia, if you want to kind of wrap up the session?
Oh, we're just gonna share the recording afterwards with everyone. And like Monica said, if any one of you have any questions, you want to follow up with her, and feel free. And I think in the follow-up message, I will share her email with all of you. Yeah,
Sounds
and
good.
thank you all for coming.
Thank you.
All right, thanks.
Yeah, see you next time.
Thanks, Monica.
Thank you,
Thanks,
Monica.
Mary and Alicia.
You're welcome.
Thank you, Caroline. Bye, everyone.
Thanks, Monica. Cheers.